In this video, we're going to design a formed intake manifold for a Honda K20 or K24. Hey everyone, this is Matt with Learn Everything About Design, and in this episode, we're going to carry on with our intake manifold design. However, we're going to do something a little bit different. We are going to talk about creating a formed intake. Now, in the last video, we created our intake using some off-the-shelf parts. We have this D-shaped 5-inch plenum. We created some runners based on off-the-shelf runner parts, and we created the injector bungs based on the off-the-shelf injector bungs. So what we're going to do in this video is we're going to talk about how to create that nice organic formed shape intake. Now, the reason that you might want to do something like this, it could be for space, it could be for aesthetics, but you really need to think about the manufacturing aspect of it. Now, the one that we have on the screen, buying some off-the-shelf 5-inch diameter D-shaped extrusion, buying some runners, and simply cutting them at certain angles or different sizes is a very easy way to build an intake manifold. It's not easy by any stretch because you still need to have some fabrication knowledge, you need to be able to weld and so on. But what we're talking about here is the difference from going to extrusions and then getting into actually creating a formed shape. So we're going to talk about how we can design that shape in Fusion 360. There are a couple different ways we can do it, and I'll talk a little bit about how you can actually manufacture it. So the first thing that we need to do is, if you want to follow along, you can download the data set you see on the screen from the description in the video. And we're going to keep everything that we have here, but we're going to reuse some of it. So we want to reuse the head flange. We want to reuse the throttle body plate. Again, I'm sticking with the 65 millimeter sort of Ford Mustang throttle body size. Obviously, you can go bigger depending on application. 65 millimeters is a decent size. I know a lot of people go to 70, 75, but unless you're feeding a really big engine, if you're dealing with an inline six, like a JZ motor 2 or 1JZs, then you probably don't need to go over 70, 75 millimeters. Obviously, it's based on horsepower, how much boost you're pushing, and things like this, but we're not talking about a crazy K-series build. You know, this 65 millimeter will likely support 300 to 500 horsepower without much issue on a boosted application. So again, I'm going to just stick with that. Obviously, if you're designing your own intake, you're going to have your own throttle body picked out, and you're going to have a plate that you need to design to match that. You can go into the throttle body plate and into the sketch. Now there is a sketch in here that has dimensions. You could easily go in and you could tweak those, and it'll adjust some of the things in here. But there will be a certain point where that isn't going to work. So this plate right now is pretty much inside of that 5-inch D shape, and at a certain point it's going to go outside and it's not going to work anymore. But what we want to do is we want to understand a bit about the way that this file is set up. Right now, the plenum and the runners are a component, which means that they have their own coordinate system. The throttle body plate and the plate at the head, they all have their own components, which contains their own coordinate system. Now that's great, and I mentioned earlier the reason I did this is because we want to reuse the head flange and the TB plate, and we're going to build the rest of the intakes based on that. And what we have here with the plenum is there are some very helpful parts that we might want to repurpose. So in Fusion 360, one thing that you can do is you can select a component, we can right click and we can copy it. And then I'm going to select the top level of the design. I'm going to right click and I'm going to use the option Paste New. Now, if we just simply paste it, what's going to happen is we create a duplicate or another instance of the component in Fusion. If we paste New, we're going to copy everything that we did, all of the features, the sketches, everything in the timeline, but we're going to sever that link. We're going to break the link. So once we do that, I'm going to say OK. And if I hide the original, you can see that we have this one here. And again, you need to be very mindful of what you see inside of your browser and how you copy things, because the comma or the colon and the number 1 after it indicates that this is the first instance of that component. You can see that this plenum also has the first instance of that component as well. If I were to just paste it, so if I right click and I paste instead of pasting new, you'll see that this new one has a 2 after it. And that's because they're exact duplicates, which means that if I change anything in the first one, it's going to change the second one. And that's not what we want here. So I'm going to take that last copy and I'm going to delete it from the timeline by hitting delete. And now we have a copy of everything that we did. The main reason that I want to do this is because we created sketches for various things, like where the plenum was going to be. We created a sketch for the actual runners, so we defined all that information, and we have the injector bungs. So this build, unlike a CNC manifold, this build is going to require a lot of hand fabrication or some creative fabrication. So it means that we're still going to have off-the-shelf components for things like the runners and for things like the injector bungs. So what I want to do is I want to build off of that. Now, at some point in time, you can go into the timeline. We want to activate this component, and you can go into the timeline and figure out what happened and when, and if you need it. So I don't need the plate on the end of the throttle body, so I'm going to delete that and the sketch that was created. I'm going to delete that split. I am going to delete the sketch that split the back. And if we expand the bodies folder, note that we've got a lot of other bodies in here. We've got the plenum and the back plate. I don't need the front plate for the throttle body. I don't need the back plate. I don't need the sketch for that. These fillets were rounding off that extrusion. This pattern is something that could come in handy, but right now I actually don't need it. I can just work with the single runner because we are going to be making some changes. And then we have to look at what else we have here. So if I go back too far, then I'm going to break some of the links or some of the information that I created. And I don't really want to do that. So there are things like the curve and the plane that we created for the fuel injector bung. And that stuff I really want to keep. But the first thing that we created was this plenum. And if I try to right click and delete it or even suppress it, you'll notice that everything else goes away. So I'm going to do Control Z to undo. So the plenum itself, this body one, has a link back to everything else that we did. And that's because we designed it a certain way, because we designed it to be manufactured by hand tools. We could use a bandsaw, we could use a grinder with a cutoff wheel if that's all we had access to. And that's how everything was sort of built in Fusion 360 and 3D. But now we're talking about building out a plenum that has a little bit more shape, a little bit more curve to it, and we don't need this plenum anymore. So what I'm going to do here is I am going to maintain everything that we did inside of here, but I want to split it up a little bit. So for example, I don't need the pattern for cutting the holes inside of the plenum because it's not going to be important to me. I don't even really need that hole in the plenum or the sketch that was used to create it. So I can get rid of that. But you'll notice as soon as I try to delete some things, it'll tell me that other things are referencing it. And if that happens, I'm going to hit cancel because I don't want to break any of the links. But what we have now is we've got the basic plenum. We've got a sketch for the plenum runner. And you can see that's why we couldn't delete that, because that sketch is actually important. And then we've got things like the sketches for the plane for the injector bung, the sketch for the injector bung itself, and then we've got the extrusion and the cuts for the injector bung. Now, at the very end, we've got this extrusion, which is cutting through the runner so that we've got the opening for the injector bung. So that's all very important stuff. Now, if you get to this point, obviously, if you're starting from scratch and you're going to design an intake manifold that is not based off these off-the-shelf extrusions, then you won't have to go through this part of the process. But a lot of times, the process of designing a part requires you to create a couple iterations of it, to create a couple variations. And if you want to reuse any of that work, like defining the profile of the runners, well, then you're going to have to think long and hard about what you need to save and what you can get rid of. Now, for me, I want to keep the runner, I want to keep the injector bung, but this body for the plenum, I'm going to right click and select remove. Now, remove will put a feature in the timeline. If I suppress it or go back before it, that body will still be there. But now I've sort of boiled it back down to just the runner and the intake bung and all the references that were used to create that. One thing that we can do to clean this up a little bit is we can select everything that we have here. We can right click and create a group. Now I'm just holding down Shift when I select those, and the group is created, and I'm going to right click and rename this group. And this is going to be called just original intake. So that way I just remember what those references are. So you can hover over that. You can see all the features in it. Within reason, if you've got more than a certain number of features, they won't display. You can see the name of it, and you can hit the plus icon to expand or the minus icon to minimize. So now that we've boiled it back down to just the single runner, we can determine where the runner is going to be and how we're going to build out the rest of the manifold. Now, the way that this would typically be done is if you're building a sheet metal intake, typically you would have a sheet metal piece that has the runner holes built into it, and you would bend the rest of it up. What we're talking about here is something that's formed and has an organic shape that's going to have to be either hand beaten over a wooden buck, or you're going to have to do some sort of hydroforming in order to get it to work. So for our purposes, what I want to do is I want to shorten the length of the runner, and I want to create another plate. And the second plate is going to be very similar to the head plate. However, it's going to be the basis for just welding the sheet metal portion of the intake to it. So the way that I can do this is I can decide where I want this cut, and I can just use a sketch like we used before. I can create a plane or a surface, but we can also select the end of the face, and we can use press pull. Now, press pull has a couple of different things to keep in mind. Now, if we just start to pull this back, in this case, let's go 40 millimeters, it's automatically going to use the offset type automatic. Now, in some cases, depending on how the feature was created, that might go back and it might edit the original feature. Now, press pull is one of those interesting tools that can actually invoke a couple different other tools. So in this case, it's invoking offset face. In some cases, it might go back and edit the extrusion. It might modify a fillet radii or so on. Now, if that's happening and you want to modify the original feature, that's perfect. The automatic will sort of pick which one works. You can do a new offset, which will create a new feature, no matter if it has the ability to modify the original. Now, you have to think about this kind of stuff because if you modify the original, what else is going to change based on it? The way that this runner was created, it was created on the D-shaped plenum, and then it was extruded to the head plate. So in this case, I'm going to just use the automatic option, and it created a new offset face feature in our timeline. So now if we look at this from the top, you can see that the runner is 40 millimeters shorter. It doesn't come all the way up to where the D plenum would have been before. And we now need to think about the plate that is going to be used to attach this. Now, this might be a good time if we're happy with the runner itself to create that linear pattern. So we're going to select the pattern option. We're going to use bodies, and it'll be the runner and the intake bung. The direction, I'm going to just simply select X. It can be a linear edge. It could have been the edge on the runner itself or the top of the intake plate. And then the number is going to be 4, and the distance between them, we're going to set the spacing to 86 millimeters. Now, 86 millimeters should give us the exact right amount. That's based on the values that were used to create the plate. And you can see that I've got all 4 runners now, and they're all the same length. Now, the good news about this, again, because we are doing this parametrically, if I decide to go back and change this offset, let's say that I wanted it to be more minus 45 millimeters, because the pattern happens afterwards, it automatically changes as well. So keep that in mind that this is pretty handy to plan out how you're doing things, because if I happen to create the pattern of the runners first and then decided to shorten them, I'd have to select all 4 faces and shorten them together. And it just takes more time, more selections, where this is a really clean solution. So now that we have the runners in place, we want to make a plate that attaches to them. And here's another thing that we need to be really mindful of. When we select a face to create a sketch, it's going to automatically project the selected face into the sketch that we're creating. Now, that is an option. You can turn that on or off in your user preferences, but by default, that'll be on. So I'm going to select that face, right-click, and create a new sketch. Then I'm going to use P on the keyboard, and I'm going to do the same thing, selecting all the other faces. We could have gone and just created a pattern, but selecting the faces and keeping the projection link on means that if we change those solid bodies, then all of these are going to update. Now, you'll notice that the projected ones bring in the center point. The center point is in the original. It's just displayed a little bit differently. It's still there for us to select if we want it, but it's just displayed a little bit differently. You can turn the profiles on and off. There's an option in the sketch palette to show or hide those, but it's helpful to know where you can click to use these for things like extrudes. So we'll be extruding through a plate or leaving that section open. The next thing that we need to do is we need to design the outside plate. Now, if we want to keep it exactly the same size and shape as the head plate, we can just bring the outside profile and project it. In this case, I think that I want to go with something that's more of an oval shape. That'll give us a more organic feel. So I'm going to go to Create. We're going to select Slot. I'm going to do a center slot, but I want to go center to center. That means I can start at the end point of this one and the end point of this one, and that'll keep those ends concentric. Now you need to think about how big this needs to be. This is going to be where the runners weld to, but also it's going to be it's going to define the size of your plenum. So in this case, I'm going to say 70 millimeters as the radius value. And actually this is, I'm sorry, 70 millimeters here, which is defining the radius value of the end. So just keep that in mind that these sizes are going to, in this case, it's going to define the size of your plenum. So now that we have this, I'm going to finish the sketch and I'm going to extrude that. Now this is E on the keyboard, but I can just take that selection. And depending on how you want to plan this, if you want to extrude it this way over your runners, or if you want to bring it this way, it's really going to depend on how you're going to manufacture this. If you're going to bring it away from the runners, you might want to add additional selections. So for example, I might want to bring in all these additional profiles. So that way the inside hole on this plate is the same size as the inside of the runner. Now, again, we could use join. I prefer for sort of just my own purposes to do a new body. And the new body is really important because we're going to be manufacturing each of these pieces, and I don't want to have to go back after the fact and cut them apart just to measure things or to create a drawing so I know what I have to do when I get into the garage and start cutting parts. I also want to make this a little bit thicker than the runners. So the runners are 0.125 inches, and I'm going to go a little bit thicker. In this case, just for example purposes, I'm actually going to go to 1/4 inch, which is probably more than I need. But I want to make sure that it's a little bit thicker than the runner. Part of the reason is I can focus the heat on this plate when welding. And this part is going to be welded to the outside piece as well as the inside piece. And if I were to make it 1/8 inch like the thickness of the runners, then what's going to happen is when I put all that heat into the outside of this, there's a higher chance of this plate warping. So if I were manufacturing this part, I would likely weld the runners to both of these plates first and try to control the heat into that plate, because heating up the inside is going to cause it to pull and try to warp. So I would probably start by tacking the inside runners and then maybe doing a full weld on the outside and sort of working my way that way before I ever attach the plenum portion of it. That also gives you the ability to go back and port the inside if you want to, or clean up the transition between here, because if we're not going to CNC these plates, if they're going to be water jet or laser cut, I wouldn't suggest laser cutting these parts just because of the tempering that would happen for the aluminum. But if you're going to have these water jet, then you need to clean them up, and the chances of the runners perfectly lining up are probably not great. Now, in reality, if I were trying to build a jig to do this, what I would probably do is build a part, in this case, the inside core that went through this plate and then sort of aligned the runner for me. So that's one way that you could do it. You could 3D print that, but it would melt pretty quickly when you try to start welding. That could also just have 4 fingers on the sides and the top and the bottom to help align it. And that's just one way you can do it. Another way you could do this is to have a portion of this plate CNC machined so there was a recess for the runners to sit into. Typically what I do, at least on like a turbo intake, is I would probably have the runners extend into the plenum. Now this plenum is going to be fairly small, so it's not really a great option. But generally, especially on a normally aspirated car, but it does help on a boosted application as well, having the runners extend into the plenum so that you don't have the surface friction on the air having to go around the sharp corner, it gives you the ability to sort of actually allow more air to come in and get a cleaner path for the air. You see this with things like velocity stacks and the way that they're designed to sort of cut that friction that's happening between the air and whatever surface you're going against, in this case, the aluminum. So again, not really going to happen here just because of space, but if you were building something like this, you can consider pushing the runners all the way through so that they extend into the plenum. This is especially helpful, again, on normally aspirated cars, but boosted applications, it does help as well. And we also have to really think about how much space there is in the back. But for right now, that looks pretty good. Now, the next thing for us to do is sort of plan out the shape and determine how we want to create it. Now, there are two sort of main ways that we can create an organic shape. One of them is going to be with surface tools, and the other is going to be with the form tools. Now, both are great options, but some are a little bit easier to use than others. The form tools are a little bit easier for us to use. The surface tools can be pretty complicated and tricky. So I'm going to talk a little bit about both, but I want to start with the surface tools because most people are more familiar with creating sketches and features. So we'll take a look at the surface tools first, and then we'll step back and we'll take a look at the form tools as well. And then you can make the decision on which is easier for you. But with that in mind, I need a plane that is exactly in the middle of this flange. Now, depending on how the entire thing was built, you might already have a plane directly in the middle, but you can see ours was centered about one of those bolt holes on the head. So I don't have a plane in the middle and I need to create one. So I'm going to go to construct and we're going to create a midplane. The midplane will be based off the top of this flange and the bottom of this flange. And the main reason I want a midplane is so that I can create sketches for the outside of the plenum. And these sketches are important that they hit at the middle simply because I created a slot and I know that the high point or the widest point of that arc is right on that plane. So now that I have a plane, it's going to be in my construction folder. I am going to rename this plane plenum mid. And another thing that we should think about is the location of the throttle body. Now, if you remember, back when we originally did this, we moved the throttle body around a little bit, and we really focused on making sure that the plenum was centered on the throttle body and all that stuff worked. Now, if you happen to be creating something where it's not centered, it adds a level of complexity. In this case, we're going to continue on with the throttle body being centered relative to the runners and the plenum. And that's going to be the easiest way forward. If you have to deal with something where they're sort of off a little bit, it just makes the job that much harder because the reference planes and the intersection points won't be as clean. But now that we have this plenum midplane, I'm going to select it and create a sketch. The first thing that I want to do is go to Create, Project Include, and Intersect. I'm going to select the bodies option, and I'm going to intersect the plenum plate that we have here, and I'm going to also intersect this body here. You could use the selection filter option if you want. So for example, if you only wanted to see the outside faces on each of these, we could select the arcs, and that would be fine. Either option is fine. Sometimes it's helpful to have the entire body. Sometimes it's helpful to have just individually selected edges or faces or certain parts of a design. Either will work fine. It just depends on what's best for you. So now that we have these references, what we can do is we can build some curves that will allow us to determine the outside shape of this. Keep in mind, however, that in reality, what we're doing is we're going to the inside face here. So I do want to make sure that at least on the throttle body plate, I also have the intersection with that face because that's where I want my curves to attach to. I want to go from the outside of this plate to here. We have to also think about the direction of thickness. So if we're going to basically thicken this outward and have a little bit of a lip or a seam there, we're not going to be that precise with it because honestly, at the end of the day, what you're going to do is you're going to design a wooden version of this, a positive wooden version called a buck, and then you would be hammering the sheet metal over it. The other option would be to build your own hydroforming rig. Now, I've seen this done with thin steel to make things like two-stroke expansion pipes. It can be dangerous because you're dealing with at least 1,000 PSI of water pressure. But in the end, what you do is you create a sort of a top and a bottom of whatever shape you want. You weld it completely on the outside, and then you attach high pressure to one end so you can basically balloon it up. It gets pretty tricky. It's much easier to do something like this, doing a hand form, it's not going to come out as cleanly as if you were actually building a production version of this and actually forming it. But in terms of doing it yourself in your garage, those are really the main two options: is try to build your own hydroforming rig with a pressure washer, or to do the hand forming method. You can get really good results with hand forming methods, and the tools, at least the basic tools, are relatively cheap. You can start with a block of wood and shape it, and then just get a basic hammer and dolly set. And probably would be helpful to have something like a leather bag that's full of metal shot or something, so that it gives you a little bit more control over the shape. There are tons of tools that you could get if you're into sheet metal work. There are lots of good resources out there, but you could really spend a good bit of money on sheet metal tools. But for something like this, again, you can do it with the basics: a block of wood. You could even just, you could rough it with a ball peen hammer and making your own sort of soft bag that you can hammer into. So again, kind of depends on what you have available to you. But now that we're here, let's go ahead and let's start to create the transition shapes that we want. Now, generally what I would do is I would use splines, and there are two different kinds of splines that we can work with in Fusion. We have a fit point spline and a control point spline. Now, the control point spline is going to give you a lot of control over the spline. It's going to, in the end, generally give you a better result. But what you're creating is an external cage that is determining the tangency direction and the weight. So if I hit escape to get off my spline tool, I can move this edge around, I can move the individual vertices around, and we are controlling this externally. So this is a great tool to make nice, clean geometry. However, the fit point spline, the points are going to lay directly on the spline. And what you get instead are going to be these green handles that allow you to determine the direction of tangency influence, as well as determining the weight or the amount of that influence. So the longer this line gets, the more that tangency pushes. And by default, the internal edges are not activated until you grab and move them, and then they'll be activated. And you can select it, you can right click, and you can relax the spline. In some cases, you can go back and select a point and just delete it to get back to a cleaner version. But again, these are the two different splines that we have to work with. It's something that you should really consider if you're going to start working with curves and surfaces, to put a bit of time into understanding how to work with the splines. We're not going to spend a lot of time there because I think it's a bit outside. I don't think a lot of people are going to be designing formed intakes to build in their garage, just because it is very time consuming. But if you really like to build stuff with your hands, it can be great to have this digital reference to help you figure out the shapes. So what we're going to do is we're going to be creating with splines, in this case a fit point spline, the guide curves to go from here all the way to here, and then I'm going to hit the green check mark. I'm going to do the same thing from here to here, remembering that we are going directly to the inside bore of that throttle body. So I'm going to hit escape to get off my spline tool, and obviously that doesn't have a whole lot of shape to it. But what I want to do from here is I'm going to take this edge, and we can either make it tangent or collinear with this projected or intersected reference, or in this case, it would work just to make it horizontal. Either will be fine. If you happen to tilt the throttle body plate and you've built this parametrically, then it might be helpful for you to actually go through and apply things like collinear or tangent relation. So either holding down Control or Shift, select both of those references and make them collinear. And we're going to do the same thing here. I'm grabbing the handle because collinear only works with lines. You could also use the tangent relationship. The curvature relationship is very similar. However, it controls the radius of curvature and the direction, not just the direction. So collinear or tangent in this case is going to give you that reference. Now, again, because we have these references here, I'm going to make these collinear, and I'm going to do the same thing here. And that is the basic shape. Now, if you want to adjust it from here, you can adjust the weight influence of the handles, or if you want to add additional curvature, you can right click and you can insert another point. So we can add a point, and then that point will allow us to move this around. I'm going to hit delete because I don't really want any internal points. The more you add, the more complicated it becomes to control. So at a very basic level, this is the curvature that this design wants. without me really messing around with the influences. Obviously, I move this handle, but if we select this and we turn on our curvature combs, we can see that we've got a really nice smooth transition. And what this is telling us is that the radius of curvature, or rather the change of the radius of curvature, is nice and smooth. If we were to pull this up and make some sort of crazy shape, then you can see it's kind of straight here. It bulges out. It actually crosses. It goes from convex to concave at that inflection point. And that's not going to be a good result. It's not going to be something that you're going to build. So what I'm really looking for when I look at these displays is a nice smooth transition from the curvature. And if you want to turn it back off, you can select it and you can just turn it back off. All right, so now that we have that, this can be done as a solid or a surface loft. So we can go to create and we can loft as a solid. Oftentimes I will go to the surfaces first, simply because they're a little bit more flexible. Surface lofts will allow you to use 3D curves as profiles, where the solid lofts will not, because it has to cap and fill the entire thing. So a lot of times the surface tools will give you a little bit more flexibility. So what we're going to do for our profiles is we're going to go from this edge to this edge. And you'll notice that when I select this edge, it only grabs at one, but I'm going to just work my way around it. And as long as those are continuous, then it'll include it in that profile. If you don't have curvature continuity across those edges, what you're going to notice is that you end up getting multiple profiles up here and it won't work. So just keep that in mind, that the base shape that you're lofting to does need to have curvature continuity across those edges. The next thing that we want to do is we want to add our rails. So down here in the rails section, we'll hit plus, and then we'll select our first rail, and we'll select our second rail. So what we've done is we've designed this lofted shape, and we've used our guide rails. When you're dealing with surfaces, you do have the option to also drive tangency or curvature continuity. Now, this gets a little bit tricky because in our case, what we're doing is we're actually driving that with our guide rails. And if we were using, let's say, a surface version of the outside of this, and we didn't want to use the guide rails, we just wanted to allow it to sort of make its own shape, then what we could do is we could drive it with tangency. In this case, it's not really going to work, but you'll notice that the shape is very interesting. It kind of flattens out here because we do have a straight edge, and it's very rounded at the opening profile there. That looks okay. It's probably not the best shape in the world, but it's not horrible either. So that's kind of the shape that it wants to take on based on what we gave it for its inputs. Now, you could spend a little bit more time. You could add more guide curves. So for example, you could go create a 3D curve from the top to maybe this edge and one to this point right here. But I don't really think it's worth the time. Again, I don't think that a lot of people are going to be designing intakes this way to build in their garage, but this is a very interesting shape. Now, from here, what we need to do is we need to thicken it. And when we thicken it, you'll notice that the plate right here, this is lining up with the outside, but at the throttle body, it's lining up with the inside. Now, I actually did that a little bit on purpose, because what I intend to do is when I would manufacture this, I would want this piece to be outside of this plate, and I would slide it down over it. And that would give me, again, this thicker base to sink more of the heat into when I'm TIG welding it. And that way the outside would have a little bit of material underneath it, and there's less of a chance of us sort of burning a hole in it. Especially if you don't have a lot of experience TIG welding aluminum, then doing something like that, making sure that you have overlapping pieces and a little bit more thickness there can really help. Now, another interesting point that we want to talk about is the fact that we have the split line right in the middle there on one side. And that's just based on the fact that to create this surface, it had to induce that split line, and that's based on where our guide rail was. Now, in reality, again, if you were to build this, what you would do is you would build the top half and the bottom half. So you would want to realistically split it in half. If we wanted to, we could use our mid plane and we could split the body in half. And I'll show you that after we turn it into a solid. So from here, what I want to do is I want to thicken this into a solid. Now here is where oftentimes these surfacing tools run into trouble, because it's only going to thicken based on the radius of curvature. So I'm going to say 0.125 inches, and you can see here that it does actually work. If you happen to have a pinch or a crease or an area where you had a really tight change in curvature, so say that spline where we had that inflection point, oftentimes that would fail just simply based on the fact that it would not be able to complete it. So now you can see that we've got essentially this section here where in reality what we would do is we would push this plate into the plenum a little bit. Now remember, we're talking about the difference of a 1/16 of an inch, so it's not going to make a drastic difference in where the throttle body is, and it's not really worth it for me to design something like that directly into Fusion. It's not worth it because it's based on the fact that I'm going to be able to perfectly replicate the shape building it by hand, which is not the case. Also note that building it in 2 halves is helpful because it allows you to make it fit the top half and then the bottom half, and you can sort of work them individually. So again, if you wanted to split this in 2, we could take this plenum mid, we can go to Modify, Split Body. We're going to select the plenum body we just created, allow it to extend that plane out. And now if we take a look at our bodies folder, we've got 2 bodies. I'm going to call this plenum bottom, and we'll call the other one plenum top. So if I hide the bottom or the top, and you can see what we've created is that thin wall version. Again, this plate would slide in a bit. This gives you the ability to, again, take a look at how far in those runners could go if you wanted them to, and adjust the entire design to suit that. So that's the basic way that we would create an organic shape with surfaces. Obviously, again, I said that you could spend a ton of time sort of making that work. Now let's take a look at how we would do it with forms. But first, let's make sure we save. For this example, I want to carry on just staying inside of this component. So all I'm going to do is I'm going to hide the plenum top and the plenum bottom, and I'm going to create a form. Now, when we create a form, this is going to be a contextual environment, meaning you no longer see solid and surface and sheet metal and all those other tabs at the top. Because when we're inside of a form, we are essentially direct modeling. There's no history. We are just sort of manipulating geometry as we see fit. And then when we finish the form, it's going to convert this T-spline body, and this subdivided T-spline body gets turned into either a B-rep, solid, or a surface body, depending on how we create it, whether it's open or closed. Now, this is a tricky process. I have a lot of videos on forms. I did an entire like 20, 30 part series on just individual tools and forms, modeled a handful of cars. They're, 10-hour video on doing a Porsche 911. So if you really want to learn forms, I suggest that you take a look at some of those other videos. I'm not going to get a real deep dive into it here, but I do want to talk about some of the basics. So when we think about the basics of a form, we could create a form based off of sketches, and we could do things like lofts, or we could create them based off of what are called primitives. And the primitives are starting shapes, and generally there are a few starting shapes that you want to go to and some that you want to avoid. Ones like the box are very good. Ones like the torus, the quad ball, these are good options. And mainly they're good options because they maintain a 4-sided face, and that's going to be important for creating good geometry. When we look at something like a sphere, the sphere comes to a point in the center and it has a lot of triangles at the top. And that generally creates a degenerative point, and you see this when you're working with surfaces, but also with these forms. And same thing with cylinder. When you try to take a cylinder and actually turn it or patch it or seal it off at the very end, then it becomes tricky because you have a point in the center at some intersection. Now, for us, ours is going to be a surface. It's going to be open where it hits the plenum plate, and it's going to be open at the throttle body. So we don't really have to worry about the sealed off part. And with that in mind, there are 2 other types that we can create, a plane or a face. Now, the face is pretty handy, especially if you have an underlying mesh, because you can snap to other bodies. And the plane will create a completely flat plane. Now, the flat plane is helpful if you want to start to create geometry in one direction before you start introducing it in 3 dimensions. But again, these are all sort of outside of what we really need to cover. So the first thing that I'm going to do is I'm going to try to make Loft work what we need to do is we need to, again, select our edges just like we did before. And then I'm going to select this edge, and you can see instantly that we get this twisted mess. Now, part of the reason we get the twisted mess is because we don't have guide curves, and it doesn't know where the point on one is supposed to match with the point on another. So we can move this point around, and we can see if we can get it to a place where it actually builds the shape we want. And we can try to use tangency to drive the direction. Sometimes it'll be going the wrong direction. You might need to use this tangency direction to flip it, and we can try that as well. And this gives us a good starting point. However, there are some inherent problems with this method. You'll notice that the plenum is not even close to matching the shape. And this is going to be a problem when you're trying to attach a form body to something very parametric like the slot shape on our plenum. Now, we can get past this by using an option that allows us to do an associative match with tolerance. But the only thing that we can do when we're creating this loft body is for us to come in and just increase the number of faces. So if we increase the number of faces in this case, it's going to be in the width direction. I'm going to reduce the ones in the length spacing because I really don't need that many. And then I'm going to start to increase the ones here. And you'll notice that as I increase it more and more, what ends up happening is it's starting to fit that shape better. We also have another option that allows us to fit the shape based on a curvature deviation. Now, what ends up happening here is you can see that we're getting a ton of divisions where we need them and not so many where we don't. But if we do something like this, we want to make sure that we're very careful about where these points are. And you can see that this is kind of twisting in space, and that twist is going to give us some bad geometry. So again, there are these sort of pros and cons, and it's not very easy for us to create shapes like this. There are certain times when they start to fall back on themselves, and you can see here, this is one of those cases. We can also come in and we can use guides. If we want to give it a guide to tell it exactly where it should be going, we can do that. Again, however, sometimes you'll note that the guide rails will cause more problems than they're helping. So if I want to use a guide rail, this is a case where we probably need to turn off tangency and make those connected, and then I can add the other guide rail to help control the shape. But again, you can see here, it's not perfect. We need to sort of move things around. I'm going to reset my width spacing to uniform, and I'm going to try to get it to rebuild this. I might need to pull this down a little bit. It doesn't seem to like the second rail, and this is a problem is because we know that this worked when we did it with surfaces, but it's not working here. So the best thing that I can say for this is let's get started. Let's just use tangency on both of these. And we can drop the tangency weight down to something a little bit lower, 0.5 instead of 1. And then we can change this to be based on curvature. Or we can come back and use associative match later. Either is going to be fine. So in order to create a nice, smooth shape, what I want to do is I want to minimize the number of divisions I have. So I'm going to take this down, and I'm going to go to 12, just to get the rough shape, 12 in one direction, 4 in the other, and I'm going to say OK. Now let's hide these other sketches, and let's talk about editing the shape. So far the shape looks pretty good. It doesn't quite have the same bulge that we had when we were dealing with the surfaces, but it has a nice smooth transition. I like the way that the edges are sort of created. But if I wanted to modify this at all, there's something that I need to think about and consider. First is going to be the display mode. Now, the display mode going between box and smooth display is very similar to when we were talking about the control point spline versus the fit point spline. The box display is going to show the external box, which is driving the tangency direction and the influence amount. The smooth display is going to be the final shape that we're going to get when we convert it to that B-rep surface or solid body. For something like this, I generally would stick with the smooth display, just so I can see the final result. But in most cases, I would say 95% of cases, I would work in the box display mode just to make sure that the underlying patch geometry, the faces, the edges, they're all good. So now that we understand how to switch between display mode, let's talk about edit form. So with edit form, we can select certain areas and begin moving them around. Now, this can get real ugly real quick. So I'm going to hit Control Z. If you want to make more gradual changes to a design, you can turn on something called soft modification. And you can see that there are different colored vertices as we go around. And what this means is as we begin to move it, those vertices are going to move with it. Now, there are, again, I'm going to hit cancel. There are pros and cons to this, but when you're creating a shape that matches other shapes, it becomes inherently tricky for you to modify something like this. Now, again, I'm not going to go real deep into forms because I really think that the majority of people are not going to be building intakes like this, so I don't want to spend a bunch of time on something that nobody's going to do. So what I want to do instead is I want to show you the match tool to get it to align to that. And we can see if we can make that work. So modify, there's a tool called match. We can turn on associative match, which means it's going to maintain a link with the geometry. And that's helpful if we decide to change the size or shape of that plenum plate. So the T-spline edges, I'm going to double click one of these edges so it goes all the way around. And the match edges are going to be this entire edge here. Now, you'll notice that it doesn't fit very well. And that's because, again, we're not dealing with tolerances and it is dealing with a uniform distribution. What I want to do is I want to make sure that we have tangency. I want to make sure that we have curvature-based distribution, and I'm going to turn on the tolerances. Now, there is a problem with this method, at least in my eyes. And the problem with this method is it adds all of these T-points. Now, T-points aren't necessarily a bad thing, but it means that it makes it harder for us to change the design later. If we wanted to change the overall shape, say we wanted to insert an edge, it's tough because this affects that and it doesn't allow us to just insert an edge halfway between these two. Again, that's a deeper dive than I'm going to get into here, but you can see associative match allowed us to match the plenum plate without having to have all of those different edges on the backside. So as a very general shape to give you a little bit of control over it, this is a decent way for us to build that. And once we're done, we can finish the form and we now have a surface body. And once again, we'll go to create, thicken. We'll thicken it outside the same amount. And now we've got this new plenum. And again, we can split it. We can use our midplane, go to modify, split body. Bodies to split is this new plenum. And I'm going to call this form bottom and form top. Now with the form body, it's exactly the same as creating a surface body or a solid body. You have solid geometry to work with. So if you wanted to add additional features, so for example, if we were to create a sketch on our midplane and I wanted to add some ribbing or a wall or something inside of here. So maybe I wanted to add a divider or something. I could just take that and I could extrude it as a solid and I could simply take it down to the object and it would just extrude down to that object. I could join them together. And if I wanted to, I could do the same thing to the top side as well. And that gives us the ability to just work with it however we see fit. So I'm not really going to keep that in there, but I did want to show that we do have the ability to do that. So we have our form version and again, we have our surface version, and they're very similar in shape. You can see that there is a difference because we didn't end up being able to use that guide curve. And I'll let you sort of be the final deciding vote on which shape you like better. You could put more or less time into both of them. So you could spend as much time as you wanted to creating intricate designs or shapes to make the flow work. But that's the general process to make that work. And now we have two different plenums that we can determine which one we want to use. For this, I'm going to go ahead and activate the top level of my design. And I'm just going to leave the form version active so we can see that. And that's the basic process for going through and making more of an organic shape plenum. Now, I did mention that I do plan on continuing this series. I want to talk about creating a full CNC version. So it would still be a top bottom like this. However, instead of being hand formed or welded, you would actually have a CNC machined part. If anybody's interested in that, it is going to involve doing a CNC machined version of the head plate, as well as dealing with the injector bungs and potentially the porting. The runners will also be CNC machined into the manifold. And I think we'll be able to get in to talk a little bit more about things like flow and design parameters. Now, I have seen CNC machine manifolds that are welded together, and there are also some that are bolted together. If you work on V8s, for example, a lot of the intakes will have a bottom section and a top section. Now, those sometimes are prone to leak, especially in boosted applications. So you have to really think about what is your end design. If you're custom making something, how are you going to get an O-ring or a gasket to seal them? You're just going to use RTV engine gasket material, or are you going to weld it together? So these are all different things to think about. But again, in that next video, we'll talk about that a little bit. If you happen to want to build your own intake in this manner, so a formed body, the best thing that I could say is to possibly get some either a 2000 or 3000 series aluminum, like a 3003, something softer that can actually take the forming shape than something like a 6061 sheet. If you try to hammer 6061 into the shape, most likely it's going to crack and fatigue and weaken. And even if you don't see that on the outside, as soon as you put boost on it, especially if you're running a high boost application, it could be a potential failure point. So definitely do some research, look long and hard at the material specs, and 3003 aluminum and some 2000 series aluminums are going to be much better for this than doing something like a 6061. So just keep that in mind, that you can't just go crazy on any material. You have to be very cautious and careful. So as always, if you have any comments or questions, please send them over, and thanks for watching. We'll see you in the next one.